Nice to email you.
Exactly, yes. All right, say welcome. So I started the stream, but I think the main thing is usually slides and these things. So if you try sharing your screen, let's see if that works.
Sure. Give me 1 sec. Does it work?
Yes. Okay, that's excellent. Then let's give people a second. But okay, oh, question. Is it okay to interrupt you in the middle with questions and comments?
Sure, sure. I
Excellent.
actually
Okay.
prefer the more interactive chat.
Okay.
So yeah, feel free to have people raise questions, and then I have tons of content, but it would be good to see.
Yeah.
Generally, I would probably gloss over the high level, but then it would be good to see where people's interests are and so forth.
Cool. Yeah. And so if people forward me questions, so just like I get them as opposed to on this chat. But yeah, I'll just interrupt in the middle. And I
Awesome.
think, oh, it's again. Let me just give you. I think it's close enough for starting. Let me start the recording. Give you a really brief info because the time is yours, and we'll start. Just give me a
Awesome.
minute. All right. So yeah, hey everybody. I'd love to introduce Hoifung Poon from Microsoft Research, where he's been working at the intersection of machine learning and its application to healthcare and treatments. Welcome, Hoifung.
Thanks so much. Very excited to be here. So should I get started?
Oh yeah, please, yeah, go ahead.
Awesome. Hi everyone. Very excited to be here. As Greg mentioned, I'm Hoifung Poon from Microsoft Health Futures. Have been working on. I come from a background on machine learning and NLP, but actually decided to work on health biomedical biomedicine 13 years ago when I joined Microsoft Research. So here I would probably kind of tell you a little bit about sort of like what we have been sort of exploring kind of generative AI for precision health, some of the learning. So let me sort of like start by kind of like give you guys a brief sort of like motivation about precision health. Which actually really motivate a lot of our research agenda centering around kind of patient embedding, which I'll tell you guys a little bit more. I will kind of review a little bit of the kind of like the generative AI, kind of like what's the current status, where it can already be helpful, and where are the major growth area. And that really sort of led us to kind of look into really two major directions. One is like how can we bridging the competency gap in individual modalities such as digital pathology, where we recently published a paper in Nature on whole slide modeling. And then more importantly is that suppose we can start to get very good model on some of those modalities, how can we actually tie all those modalities together in multimodal reasoning? And I will conclude with some kind of real-world applications. So please feel free to interrupt with any questions and comments. I really love this to be an informal chat rather than, sort of a formal lecture per se. So I think many of you have been familiar with the concept of precision medicine or precision health, right? So obviously that in the ideal world, we really want everyone to be able to respond to the treatment they have been prescribed, which has been signified by the blue person on the left here. In the real world, unfortunately, many patients, don't respond to the treatment identified by the red person. So this is obviously a huge problem with a lot of waste and unnecessary suffering, but most important of all, it's just a giant miss of treatment opportunity. And so cancer is really sort of like the poster child for this problem. And the first generation cancer treatment is dub/burn and poison, right? The toxicity is very high and the efficacy is low. Then bring us to really sort of like the second gen of targeted therapy, right? So apology a little bit about the imagery here, but on the left, you have a patient who with late stage melanoma where nothing works, right? And in the middle, you see the patient undertaking a drug that specifically kind of target the mutant protein domain for that drive the patient's cancer, right? So that's sort of really the dreamland of precision medicine, right? As you can see, at that where the tumor basically melted away with almost a very minimal side effect. Now, unfortunately, cancer is one big secret weapons, right? As many of you know, which is natural selection, right? So after a while, it figured out how to, circumvent the treatment and then come essentially roaring back, right? So so then came sort of like really the most recent and the cutting edge treatment, which is the immunotherapy, right? And so the whole idea is to mobilize the immune system, which is the one health system that also has a blessing on natural selection and can counteract a lot of those kind of mutation and variations. So indeed, you can see one of the representative drug called Keytruda by Merck, right? So that really can work miracle on some of the late stage cancers, and then lead to really the blossoming of a whole swoop of kind of immunotherapy, especially checkpoint inhibitors, right? Unfortunately, if you look at the global picture, however, if you look at actually all the patients, right, Keytruda actually only work for a minority of patients. The response rate hovering around 20 to 30% for most cancer types. So this is very kind of frustrating, right? And then once the standard of care fail, right? So then the best hope really lies into clinical trial, right? So here is Martin Tenenbaum, who is a very accomplished AI researcher and e-commerce entrepreneur. At the peak of his career, he was diagnosed with late-stage melanoma. And fortunately for Marty, he mobilized his network to help find a trial, which saved his life, right? But most of the cancer patients are not so as lucky, right? So in the U.S., actually, less than 3% of patients actually were able to find a matching trial, and whereas on the flip side, a lot of cancer trial failure simply stem from the fact that they couldn't enroll enough patients in time. And then if you talk to a farmer, obviously the perennial challenges is that developing a new drug costs just so damn much and takes so long, right? So fundamentally, what we really want to sort of like tackle a lot of this kind of problem is to have a sort of like continuous learning health system which can actually really incorporate any sort of like health information signal back into the system to optimize care and accelerate discovery. So a key underpinning that we have been working on for a long time is this concept called real-world evidence. So every day, if you think about a hospital, a doctor, right, office, right, there are literally billions and billions of data points collected about patients' diagnosis, patient journey from diagnosis to treatment to outcome, right? And before the patient journey start, right, a doctor, even the best doctor, may not have any idea what exactly would the disease progress, whether the patient actually might respond to the treatment, right? So in some sense, each journey is like a mini trial, and then each encounter really bring new information, right? So if we can harness all of this kind of information, is essentially sort of a population scale free lunch, right? So real world evidence, obviously the concept is not new, all right? So people have been milking, structured data like claim code for decades. But what's actually really exciting is that with the advance of generative AI, we now can actually start tackling much richer information sources other than just readily available structured data. Right. So, for example, here is a DID journey for cancer patient where each bar is one clinical notes, right? And the notes actually contain lots of, great information about the patient. More importantly, there are lots and lots of other information-rich modality, right? For example, a cancer patient journey typically started from, non-invasive stuff like, CT, MRIs, and so forth. By the time you get biopsies and recession, you will start to assess, for example, digital pathology, genomics, and so forth. And then there are fancy stuff like multiplex protein, spatial transcriptomics, and a growing array of new kind of sensors, right? So each of these modalities is trying very hard to tell us something about the patient, but each of them are also inherently limited, right? So I really like to liken thinking about this as really sort of like all this kind of blind folk touching the elephant, trying to figure out only by actually assimilating all those information, we can recapitulate the elephant, right? So to some extent, this is sort of like our nerdy way to think about precision health, right? Which is like fundamentally, we just want to basically learn a function, right? That starting from the input of all those multimodal kind of patient journey, and then essentially try to predict, disease progression, and then treatment response. And so the challenge is that the patient journey could be sort of like really kind of like longitudinal and so forth, right? And more importantly, many of those information actually we never get to see, right? In some cases, there are sort of like this kind of principle of uncertainty, right? So if you actually assess a particular modality for a tissue sample, you actually literally destroy the sample, so you cannot assess other modality, right? So that really sort of like is one of the fundamental or the challenge for how do we actually be able to learn about kind of precision health, right? So one of the promise for generative AI, right, in particular with generative model, is that if we can learn a generative model about a patient journey, right, then we can potentially start to predict those missing information based on the observed information. And in particular, all the next medical events are really just essentially a special case. So that essentially leads us to our overarching research agenda, where we essentially want to train sort of like biomedical frontier models, right, from population scale real world data. And here, where the Gen AI actual disruption means that it's now we really have a very, very powerful tool from the generative model, right, to be able to learning a high fidelity patient embedding that can almost serve as a digital twin for the patient. And if we have some, yeah.
So in the challenges you described, it's longitudinal and sparse, but you didn't mention biased sampling, which seems for medical, where treatment effectiveness is important.
Absolutely.
That would be the critical issue.
Absolutely, absolutely. So you are spot on. So there are lots of and I didn't mention that also the missingness is not random, right? And then everything is noisy, right? So the imagery could be noisy, right? I mean, early days, right, when you do microarray, actually the result could change depending on morning or the afternoon when humidity is and all that kind of stuff, right? Clinical node could be very noisy, right? So we tend to think about doctors node could be gold standard. Actually, it's far from the case, right? So if you talk to enough radiology or pathologists, right, they will tell you the horror story, like, they may not agree with themselves 6 months ago, right, or maybe a week ago, right? So by looking at the same image, so that's absolutely a big challenge underlying all this information is that we have to assume that all those kind of information have noise, right? Now, on the other hand, if you think about it, I wouldn't say that's so different, so special in biomedicine, right? Because if you look at like climate modeling, you look at like, speech recognition, right? Like, you look at all the classic generative model application case, you have to assume your input, observable input are noisy, right? So the question though is that what's the underlying structure of the noise, right? Does overall the signal outweigh the noise? That's probably the most important part. And so first of all, the signal has to outweigh the noise, right? So that's partially why preventive, medicine is so difficult, right? So early detection is so difficult, right? And then also, if you know about some of the structure of the potential noise and biases, like you said, right, then we can at least start to play in some safeguard to detect whether there are those kind of biases. We can also maybe in some cases even leverage those known structures, sort of like prior, right, that you can inject into a generative model. But that's absolutely the some of the frontier topics.
So noise makes sense, and I think right now you're the way you're describing it, you're thinking of unbiased or mean zero kind of uncorrelated noise. Well, then this actually makes a lot of sense, and also climate is that way. But what I have in mind is biased noise, where what a given surgery is given to people who are sick. You do not give it to people who are not sick, because that would be unethical. But that means that your data set, the dynamics that you're watching, are correlated with the attributes of the people who you're treating. How do you? I mean, and I'm not aware of causal inference technologies being applied to generative modeling. That connection has not been made to my knowledge. So how do you deal with that?
I actually hold your thought until the actually at the end of the talk. I actually will talk about how do you also potentially incorporate causal inference. But what you actually mentioned here is spot on. So many of you know that the gold standard for medicine is randomized control trial, right? And randomized, and in many cases, you also ideally you even want double blind to minimize, human bias, right? So treatment bias. So and the randomization is the key, right? Because that's actually where you can eliminate a lot of those just spurious correlation, right? So what you are hitting on here is actually sort of like the perennial nightmare for how do we use observational data, right? So because you can kid yourself by mistaking correlation with causation, right? So and in July, there is a peak of ice cream consumption. There is also a peak of heart attack, right? So but ice cream obviously doesn't lead to shark attack, right? And so that is actually sort of like definitely one kind of like emerging growth topics. I can actually towards the end I will give you some example that I actually didn't prepare very detailed, but there is some recent research we have done to show how you can incorporate some of the causal inference to kind of like minimize those bias, right? So there is, we actually sort of assess how you can minimize those. And then we show that actually by doing that, we can actually using some of the real world data to even simulate some of the previous published trials, right? So,
excellent.
Yeah.
All right, thank you.
Yeah, wonderful question. Please feel free to interrupt me. With more questions and comments. So, so here's sort of like if we have this kind of patient generative model, right? That we're able to create this kind of digital twin. Now, one of the most immediate ramification is that we can start to play kind of like patient like me reasoning, right, at the population scale, right? And when there is a patient with cancer, for example, unfortunately, right? So people obviously the first thing to do is try to look for a second opinion, third opinion, and so forth. But if we were able to kind of like do this at the population scale, and with the patient embedding, you can snap your finger and get like really 5 million opinions, right? You can gather all the similar patient, interrogate what have been tried for them before, right? And what works and what doesn't work, right? So you can immediately improve patient care. But most importantly is that you can also start to unveil what the current kind of like health common sense doesn't work, right? So where the treatments start to break down, right? So by comparing the responder, for example, the Keytruda responder, exceptional responder versus a non-responder, right? And at the minimal, you might be able to figure out, better patient stratification, which you can then improve the companion diagnosis. But you might also be able to, uncover some of the underlying, differences between these two groups, and then figure out the underlying, kind of like mechanism, explain the differences, right? So in this way, you can really also accelerate kind of like the biomedical discovery. So in some sense, you can think about like, I mean, imagine if you have frontier model that consume the entire web, right? Read every single, guidelines and textbooks and what have you, right? Would that be sufficient, right, to be, super duper medicine? Arguably, it's not, right? So give me one second. Um, sorry, I need to let the cat out of the office. And so arguably that super duper kind of medical brain, right, still are constrained by the glass ceiling of today's healthcare common sense, right? Now, what we can do potentially by learning from population scale data, by really unlocking all the insight buried in that kind of population data, is potentially we might be able to unlock sort of like emerging capabilities, right? And I mean, you guys have, show a lot of the great work in the, but you can imagine that can we actually smash the glass ceiling for the today's healthcare common sense, right? I mean, think about how horrible medicine looked to us 200 years ago, right? Maybe in 20 years we look at today's status and we realize that how primitive we are today, and but how can we actually really accelerate the progress? Partially, like, I mean, the challenge is that we cannot afford to run, randomized control trial for, left and right, right? So that's really one of the big bottleneck. But maybe we can actually using this population scale real world evidence to really kind of augment, randomized control trial to make medicine advance much, much faster. So that's kind of like exciting, but there is obviously a lot of challenges. Early last year, obviously, everybody want to get on the Gen AI bandwagon, right? So this year, people start to question about, okay, are we actually, hyping ourselves? I would say, obviously, there are inevitably some high curve, right? So, but there are also some area where, Gen AI can already deliver a lot of stuff to help advance the precision health. The first thing, I will give you some example, but obviously you guys have done amazing work here as well, right? So it's this concept I would call universal structuring or universal abstraction, right? So it's essentially just structuring the clinical notes, right? So because the bulk of the patient detail information actually captured there, right? And there are not enough abstractor, curator, registrar to pull out those information, but Gen AI can actually now hold the promise, I would argue already 80-20 be there. You can also obviously using it to translate between language, but more importantly for biomedicine is that to translate between ontologies, right? Like OMOPs and FHIR, frontier model knows them actually by heart, right? So that actually have a subtle but very major implication on interop. You can also using that to, essentially think about it as a smart, kind of like knowledgeable intern to some extent, right? And you can actually start to using those frontier model to kind of like annotate, data and evaluation. Later on, I will show you some example in LavaMat, right? So, but there are obviously tons of other great works still. And the most exciting thing is that obviously using that to reason and talk to the data, right? So I wouldn't belabor you guys about some of these advances. Just briefly mention sort of the one kind of really 2-week hackathon we did in Microsoft Research that produced a map prompt, and to show that really what we get them really want to do here is to say, hey, what if we don't do any fine tuning? What if we don't change any weight, right? How much can GPT-4 actually do, right, in kind of like biomedical exam and so forth. And turns out that it can do it very well. It can do very well on many of the NLP tasks, and overall, obviously, they are really proficient in biomedical text, right? So, and if you think about it, it sort of really makes sense, right? So because the public web actually have tons of biomedical text there, right? Just PubMed alone. Um, um, Many of you know that my, prior life is try to milk stuff from, PubMed, right? So PubMed alone have 30 million papers, but you also have tons of web pages like WebMDs and all those kind of stuff, right? You have, all those other kind of sources. So it's not surprising, probably from the inside, how this kind of generic, frontier model, how they are really strong in biomedical text. So here's one example. So we talk about clinical trial matching, right? One of the bottleneck obviously is understanding all those like elaborate inclusion, exclusion criteria. But you could basically give a very natural sounding instruction, and actually GPT-4 or many of those frontier model can actually interpret those elaborate, including the very sophisticated and or not logic, right, for you. And then on the flip side, right, so obviously the biggest bottleneck is actually in structuring the patient records, right? So here, actually this frontier model can literally read the freaking manual, right? So you can pretty much put a guideline, annotation guideline, into the prompt, and then along with the patient notes, right? And many of this we have done some of this experiment, right? For example, with really sophisticated clinical staging, with RECIST criteria for disease progression, and even just simply out of the box zero shot, it can do very well. If you give it a few shot example, if you tweak it a little bit on the chain of thoughts and all those kind of stuff, it will work really well. So long story short is that on the text side, right? So probably a very kind of like one takeaway is that it can already serve as a very powerful tool to kind of like essentially bridging the challenge for structuring those all those unstructured clinical biomedical texts. So that leads us to yeah, go ahead.
So to what extent is GPT-4 or similar models are aware of medicine, actually? So, I mean, to some extent, obviously they are. They've read the papers that discuss the progression of disease, but to some extent they're not. I mean, I'm thinking of simulations of the vascular system that pump, blood through fake simulated vessels. That's far more precision than GPT could ever have. So where is it now, and how can it be extended?
Yeah, let me first clarify. Here, I'm strictly talking about universal abstraction. What I mean here is that the text have some information. So basically, information extraction, right? So in biomedicine, there is a huge workforce where their whole job, right, is a very boring, repetitive work. It's like, let's look at this 200 notes, right, and let's figure out, okay, what are some of the key information, right, we need for the patient, right? So what's the staging for the cancer, what's a biomarker, what's a prior treatment, and all those kind of stuff, right? So here I'm when I say progression, what I mean is that there are this kind of guideline to say, let's say a patient take 2 CT, right, in 6 months apart, and then radiologists look at them, write a report, right, and then you can, the report will basically say, hey, here are how many lesions, how big is the largest lesion, and all that kind of stuff, right, and then there is this guideline to say, based on, how the lesion evolve, right, is it a stable disease? Is it a progression, right? Is it a remission and all those kind of stuff? So here, what I'm just saying is that the frontier model simply follow those annotation guidelines based on the text report, right, to determine the progression. I'm not saying that the frontier model, we're using that to actually be a digital twin to simulate the patient progression. So does that clarify, first of all?
It does, but I actually am asking about the digital twin simulate use case, because it seems like you're heading there. And
Mm-hmm,
if we
mm-hmm.
get to, do you have an idea of how much it knows already from just reading the text, and how much it doesn't know and we need to be acquainted with?
Yeah, so great question. So I think if you are saying, hey, I am just seeing all the notes, right?
Hmm.
I would say that today's sort of like the simulation or digital twin, it's very, very limited, right?
Hmm.
And the reason I said it's very, very limited is because that, think about the source of the information. That's basically what I try to make the point is that at best, right, you are basically synthesizing all today's health common sense, right?
Right.
So that's already very impressive.
Hmm.
Make no mistake, right? So that's probably infinitely already way better than maybe some of the average doctor, maybe even could be above some of the even the best doctor, right? But that still have that glass ceiling, as I mentioned earlier, is that that's still like what people think about healthcare common sense. But uh, what we actually heading towards is like, what if we look at the raw input, right? So because here we are just talking about here are all the human interpreted input, right, of all the nodes and so forth. But I think the dream would be like when you look at the raw input, let's say a radiology or digital pathology, you may be able to discern a lot of patterns that even the best doctor don't actually know how to discern, right? And also today's medicine is governed by obviously those medicine that you painstakingly gather from all those RCTs and so forth, right? But that's a very limited kind of like probing of the patient journey, right? But if you truly can get, all 8 billions, journey, right, you may be able to discover a lot of the kind of long-term kind of like outcome, how they correlate with the input. Maybe you can start to uncover some of the causal mechanism. That is the digital twin, I think, will be much, much more powerful for the next generation. Does that make sense?
Yeah, it does. Yeah, that's exactly what I was wondering about. Thank you.
Yeah. Yeah. And so that's actually a perfect segue because on the text front, we already talked about how the frontier model are very powerful. But once you go beyond text, then it's not very hard to find things that where today's model, did very ridiculous stuff, right? So they may have a very kind of superficial notion about what would be CT or digital path and so forth. But once you drill down to some of the details, they really have no idea. And to some extent, like that's not really hard to understand, right? Because unlike sort of like pure biomedical text, when you think about what does it take, right, to start to figure out all those minute detail about multimodal, about a patient, then you start to need to have those multimodal longitudinal patient data and obviously those kind of data are not flowing in the internet, right? So and for good reasons. So that's kind of like a perennial kind of like competency gap. So you can think about sort of like most of my remaining talk is to figure out trying to see what's the best efficient way to kind of bridging those competency gap, right? So I would say there are really two big problems. One problem is that biomedicine actually have a plethora of kind of like modality and keep growing, right? So every other day I talk to some of the biomedical folks, I learn something really exciting, right? They come up with some fancy new technologies and some of the older technology actually become more affordable. So now they become scaling and so forth, right? But many of this modality are really have very different characteristic from sort of like what the general domain AI, right? So it's working on. Medical imaging is a great example, even though it's called imaging, right? So there are lots and lots of different kind of modality underneath it, and they are also very, very different from web images. So I will give you sort of one example by digital pathology, but there are many other modalities. Now, another challenge is that each of those modality essentially is one of those blindfold, right? Trying to tell you something about the elephant, right? But unfortunately, each modality, when you learn it separately, right? So it basically using a different language to tell you about the elephant, right? So you basically then get a United Nation of all the modalities, right? So, and each speaking in different languages. So then the really holy grail challenge here would be, how do we actually enable crosstalk among those modalities and so forth, right? So and I would also show some of our kind of hypotheses and what's our bet here, try to tackle those challenges. So for the interest of time, I will kind of go a little bit quicker, but feel free to stop me if there are any particular area you guys are particularly interested in, right? So if you look at immunotherapy, right? So what we have today is very, very promising, but also very, very frustrating, right? So and the response rate is a minority, and also our companion diagnosis is too simplistic, right? So maybe look at PD-L1 expression, maybe look at tumor micro mutation burdens and so forth, right? Very simple kind of classifier. What we actually really want, right, is to actually model tumor microenvironment, and that's what digital pathology brings you, right? So many of you are probably familiar, right? Digital pathology, you've got a tumor core, right, from biopsy or recession. You cut them into thin slices, do some chemical on them, and that will start to reveal all sorts of structure that you care about, right? The most common one, the H&E, right? So basically give you the cellular and cytoplasm, right? So essentially the cell structure. From the cell, all those morphology, you can often discern sort of like, you know, individual different cell types, right? So including, for example, the tumor cell, right? Melanoma here, or the lymphocyte, which is the immune cell, right? So, and the tumor, that actually respond to immunotherapy, right? It basically often happens when the immune cell actually deeply penetrating into the cancer, right? So that means that immune system already know about there is something wrong there, and now you mobilize them, then they wipe out the cancer. On the other hand, there are other cancer called so-called cold tumor, right? So where actually the tumor recruited a bunch of immune cells surrounding it, right? Creating a protective, you know, shell, and to tell the immune system to back off, right? In that case, you mobilize immune system, obviously then it doesn't know where to go and basically destroy the normal cell and causing autoimmune withdrawals and maybe even kill the patient before cancer, right? So modeling this kind of tumor microenvironment is very, very important, right? And that means that we really need to try to figure out how to model this kind of super global kind of patterns, right? And theoretically, obviously, like we have a very powerful tool, right, invented by you guys, right? So which is a transformer, right? So and essentially one way I think about transformer is that it's basically enable every pixel to passing messages to every pixel, right? So that's what the layer basically unroll the messages, right? And that really allow you to essentially capture arbitrary complex kind of like dependencies, right? So that's very promising, but there is a one big Achilles heel, right? Which is that if you have to do that message passing between every pair of pixels, that means the computation grow quadratically in the number of pixels, right? Digital pathology, unfortunately, some of the largest images in the world, right? So, and if you print a very standard kind of digital pathology slide, right, by standard printer resolution, right, my pathologist friend told me that it will basically take up a whole tennis court, right? And it can easily be hundreds of thousands of larger than any standard web images, right? Which means the computation will be billions of times larger. Right, so here we are basically trying to leverage one idea that has been long explored in the speech community, which also have long context, right? Called the dilated attention, right? So here the idea is actually really simple, right? Self-attention doesn't kill you if the block is small, right? So in fact, that's why it works for many of the normal contexts, right? It starts to kill you when the block gets larger and larger, right? And the computation grow quadratic in the block size, right? So what we can do is that for a local block, right, we can say, okay, you guys pass messages as normal, right, between every single pair of pixels, but after you do that, right, so every pixel in that block, right, so essentially already get a lot of information about the neighborhood. And then now when you come to try to passing messages in larger block, right, between kind of pixels that farther away, right, then you will say, okay, maybe I don't need to have every single pair of pixel to pass between messages, right? Maybe I can actually take representative of local block, which already know a lot about the neighbors, right? So, and then just passing messages among the representative, right? And then we can choose the sparsity of the representative proportional to kind of the block size, right? So that perfectly cancel out the quadratic growth. That's basically the idea behind, right? So it's a pretty simple, straightforward idea, but adapting that to digital pathology is actually the journey is super hard. And actually a lot of the time, right, as many of you work on real world data, right? So actually getting the data, figure out, all the politics and all those kind of stuff, actually aligning stakeholders and so forth, that's the most difficult part, right? So for us, it took us more than 2 years to essentially work with our collaborators in Providence, enable them to be able to actually get those data in computable forms and so forth. And then the actual modeling is basically a summer internship, right? So, and we are very, very lucky to have amazing collaborators in Providence and University of Washington, Shengwang's and teams there. So we were able to train essentially the first host slide pathology foundation model on close to 200K host slide, which amount to over 1 billion image tiles, right? And so obviously the one thing that we want this kind of foundation model to do is to be a Swiss Army knife, right? So to be able to out of the box start to be able to actually shortcut a lot of the downstream tasks. Now, what we really care about, right, is obviously the human microenvironment, the global context, the long-term survivals, and all those kind of stuff, right? But one challenge in pathology evaluation is that most of the standard benchmark, right, are actually tile based. So that's partially because of that computation challenges, right? So people often, sensibly try to focus on smaller patches, let's say 256, right, and so forth, but that basically limit you to some of the much simpler tasks, right? So so here we obviously have to do some of those kind of like, standard kind of tasks, right? So for example, cancer subtyping is like, let's say you have a slide, right, for ovarian cancer, and then can you determine whether it's one of the 6, major subtypes, right? So you can imagine that obviously like the gap between global modeling and the patch modeling for this kind of task, right, is probably smaller, right? Because subtype by definition are defined by morphology by pathologists, right? And by definition, it should be discernible from the morphology, right? So here we still interestingly, we were still able to find that there is some kind of significant improvement, right? Compared to if you just like looking at the patches and then do some very primitive way to aggregate them, right? But obviously this is exciting, at least like showing that for run-of-the-mill tasks we can already do quite well. But what we really want is obviously the holy grail to model the global pattern. Unfortunately, there were not that many that kind of benchmark, right? For example, can you actually look at the slide, correlate with the the long-term survival after the checkpoint inhibitors and so forth? We're trying to create some data set ourselves with our collaborators, but that's still work in progress. So in this Nature paper, we basically take sort of like a surrogate task, right? So the surrogate task is that given this slide, can you predict the tumor mutation status, right? So for example, does the tumor KRAS gene has a mutation or not, right? Based on the host slide. Now, people have obviously looked at this kind of task, but what people tend to focus on are very specific cancer type, very specific mutation, right? So for maybe a couple of them, right, there is a well-known strong correlation. But for the most part, right, things are pretty much unknown, right? Especially when you talk about pan-cancer kind of like mutation kind of signature, right? So we basically try to tackle the most, really it's the most difficult mutation prediction setting, right? Including sort of like, can you find signature, morphological signature across very different cancer types, right? That we hypothesize at least that really try to stretch the boundary beyond the tile level modeling. So here, as a sort of like, we basically confirm that indeed, this is where we actually outperform a lot of those kind of non-host line modeling by a lot more, right? And then subsequently, folks like, for example, in Mount Sinai and other places, they also make a very similar observation. And this is sort of really exciting because for a lot of this kind of gene, right, mutation, you don't even know whether there is a discernible morphological changes, except for some very special case like maybe microsatellite change in colon cancer, right? There you actually see very distinct patterns, right? But most of the time you actually don't know. And here we even uncover some pan-cancer signal, for example, with very important gene like KRAS, right? Where our pathologists collaborate, have no idea about, and got very excited, right? So that's sort of like at least a glimpse of hope that we might even be able to discern something beyond the human experts and so forth. But obviously we are far from being done, right? We also did some, obviously, very standard kind of clip training, right? Based on the slide and the reports, right? And essentially using the report as a natural language supervision and show that you can actually do a zero shot for some of these tasks quite well. But all in all, like one thing that really surprising is that digital pathology is sort of a niche domain. We are pretty surprising to see so much interest from the community. And we also sort of saw all this download from all over the world. That's really motivating for us to kind of like do more here. But at
so question about that model. So the trick you played
yeah.
was obviously the multi-resolution thing, which seems like it smells like a very transferable trick. Actually, I'm thinking whole universe simulators do exactly the same thing. It's a fast multipole where they just say, approximate that part of the universe very coarsely, this part of the universe, precisely.
Absolutely.
And I'm also
Absolutely.
thinking climate has exactly the same trick because around
Absolutely.
the outside of the Earth or a long time ago, you want to coarsely approximate. So
Yep.
what other connections do you see, or diffusion models? They
Yep.
kind of, you have a neural approximation based on, a regional state, like as you can coarse grained, fine grained. So what directions do you see for improving this direction?
Yeah, you're spot on, right? I think one of the really fascinating notion, I come from NLP. There is a great work in NLP called actually cost to find parsing, right? In fact, actually one of the main offer is actually in Google, right? So Slav Petrov, and so actually know him well from grad school days. And the idea exactly like you said, to think about there is this multi-scale kind of phenomenon, right? And then how you can start from sort of like really combining coarse level and then be able to also actually capture every single scale. So climate is one obvious thing. And I think really sort of like in generation is also very similar, right? So image generation, like you said. So yeah, honestly, I have this kind of fish eye vision to mostly focus on health. So I definitely think about lots of cases in health. One of the obvious case is actually the time scale, right? So when you think about modeling a patient journey, in some sense, it's kind of analogous to modeling climate, right? So there are short-term weather, there are long-term climate, right? So and I think right now, we are unfortunately limited a little bit more in the medicine side, right? In the, for example, focusing on the clinical footprints and mostly sort of that limit us to a little bit of the more short-term case, right? But if you think about like that worked reasonably well for cancers and other high touch kind of disease. But when you go to things like mental health and metabolic disease and all those kind of things, right? So much footprint actually are captured outside of clinical footprint, right? And also really require you to start modeling at the multimodal scale, right? So what will the patient do in 3 months versus what will patient do in 30 years, right? Certainly, like, I see a lot of potential there.
Excellent. Thank you.
Yeah, cool. So in the interest of time, I would just quickly sort of like kind of sketch some of the remaining high-level ideas. So in a single modality case, right, obviously you can basically apply this general autoencoder-ish kind of scheme, the recipe, right? And here is actually where you can also encode some of the prior knowledge about the modality, right? So in early days vision, obviously dominated by convolution, which is basically one intuition about some of the structure, translation, invariance, and all those kind of stuff, right? Once you dive into each of those modalities, right, you will be able to see amazing potential kind of like structure. Like, for example, CT versus MRI, right, versus ultrasound, versus pathologies, and versus, multiplex proteins and all those kind of stuff, right? So and there is really so many exciting things to look at this, right? And obviously encoder and decoder can be the same and so forth, and we probably don't want to retrain some of this. We don't need to reinvest in the text modality, but can focus on the non-text modality, right? But still, that assuming we did really well in basically kind of like do nonlinear dimension reduction for all those modalities, right? There still leaves the challenge here is that each of them, again, is trying to tell you something about a patient, but in a distinct language. So, for example, CT may be encoding maybe a tumor lesion in some weird place in the embedding space by itself, right? Digital pathology maybe in some other very different place in the embedding space, right? And so if you just take the raw foundation model train, right, then there is very difficult to actually reason across them, right? So I'm an NLP guy, so I have lots of friends in translation who educated me about, how, the translation world, right? So the world have hundreds of languages and so forth, and how do we do the translation, right? So obviously, like, you can't rely on brute force, right? You can't do pairwise translation, right? So you take a language from Africa versus a sub-language in India, right? There may be zero parallel data for them, right? So obviously the common trick for all the commercial MT system, right, is that you basically take some resource-rich language, typically English, right, using that as a interlingua. So now the language from Africa, you can translate to English, then translate to the sub-language in India, right? So then you can successfully scale to hundreds of languages in the world, right? So here, our idea is very simple, right? So it's basically we say, hey, maybe we can do the same thing in multimodal. Maybe we can basically take one modality, right, and then ground it everything else to that. And so for many reasons, right now we are betting on the text modality, right? So there is already amazing foundation model reasoner for that, right? And also, if you look at any modality under the sun, right? So the chances are the study of that modality is conducted in natural language. So that means that it will leave paper trail, right? It will leave some of the modality text pairs, which you can essentially leverage as a free lunch. So here the idea is really simple, right? You can, align that with sort of like paradigm like late fusions and so forth, right? We have all those encoder and decoder that separately train for individual modality, right? We basically maximally try to leverage them, but then focus the learning to just adapter layer that basically do the translation, right? So there is a subtle but very different major departure from the clip model, right? So clip, you basically do, here are two modality, you treat them the same, you push them to a common, like interlingua, a new common interlingua, right? If you only have two modality, that's easy, right? Once you have three, you got a three-body problem. Once you got more and more, right? And so in this way, by grounding in into the text modality, you basically circumvent that challenges. Now, obviously, there was many limitations in this paradigm, right? So the jury is still out. We have some promising progress, but this is far from being concluded, but this is essentially the direction we're heading in right now. For the interest of time, I'll skip a bunch of stuff. I would just highlight the LavaMed, right, which many of you are probably familiar with. That's our first attempt, right, to try to explore this direction by focusing a lot of our learning in the adapter layer, or you can call it projector or what have you, right? We also publicly released a model, but as I joke often with my team, it's like any model release become obsolete these days, right? So, but what's the really lasting value is the general recipe it represents, right? So one is this modularity principle, and then using text as an interlingua. Another kind of like very commonly applicable recipe is to using some of this powerful frontier model to actually generate synthetic data, right? So that actually can really power a lot of this kind of training. For the interest of time, I will skip all this. I will mention that we have also tried on radiology, right? So once you go beyond the public data, right, public image and text pairs, right, you go to a patient journey, there was so much kind of image text data, right? So obviously many of you have done amazing work here as well. And you can also add an image decoder to this scheme, right? So, and in this way, you can essentially basically like, hey, given a CT scan or a chest ray taken 6 months ago, right? If you said, hey, here's the progression, right? What happened in the next image, right? So you can imagine could be a very interesting exercise to force the model to learn very intricate image, evolution interdependency, right? You can also switch the image decoder to a mass decoder, right? Here we basically we are inspired by SAM, right? But we are also thinking that a lot of the default application there is to have a bounding box and then basically figure out what's inside, being quite agnostic about the object types and so forth. So here we basically try to take an opposite direction. It's like we try to maximally leveraging the information about the object, right? So the tumor core versus organs versus enhancing tumors and all of that stuff, right? And we try to basically do a joint recognition, detection, and segmentation together. This is why we call it image parsing, right? And then we've essentially grounded everything on text, unifying text prompt, right? So obviously this is just a baby step. Quite excited about progress, but much more need to be done. And ultimately, I want to conclude by saying that if we have the patient embedding, right, then we can also start to train embedding for other stuff, right, like intervention. And then we can start to think about the whole medicine being essentially matching reasoning across those embeddings, right? And here I want to just show you very quickly about clinical trial matching. We already showed that this actually can work, right? So many of you know Providence is the third largest health system in the US. So very excited that they start already using some of our work and from research to start piloting with real patient. But what this actually means is that it's way beyond just clinical trial matching, right? Clinical trial matching by itself is already $1 billion business, right? But the really ramification is that if you can do this, if you can conjure up virtual cohort by snapping a finger, right, then you can actually using this as a hypothesis generation. So I don't have time to talk about the causal reasoning, but that make a big difference here, right? So to grab your earlier comment, but I just want to share this paper. Feel free to check it out. Where obviously still very, very baby step, but we show that by incorporating causal inference, we can actually simulate many of the marquee lung cancer trials using real-world data from Providence. I will end with sort of a sobering note, right? So here's the identified patient journey, starting by some CT, chest ray, CAT scans, and so forth, then MRI, and then starting the treatment guided by the chest ray, right? For 8 months, the patient looks like fine, right? But then the patient starts developing some new complications. And then unfortunately, then we figure out that the cancer actually metastasized. and then within a month, the patient died, right? So that basically is sort of like if you stare at the kind of patient journey, you see tons of this kind of example, really heartbreaking, right? So, and we can't help but feel like we are at the cusp of actually potentially making some difference here, right? So early on, I told you about sort of like we really already, Gen AI already having a lot of progress on the left-hand side, right? So automating the mundane chores and so forth, following the guidelines and so forth. But what's really exciting is actually really on the right-hand side, where can we automate discovery, smashing the glass ceiling of today's healthcare common sense, right? Inventing new guidelines in real time, or so that's really like where we. So want to highlight my team who really do all this work, and also all of our amazing collaborators. Thanks so much.
Oh yeah, well, yeah. Thank you very much. This was fascinating. If anything, let me just ask one final topic: is yes, the causal inference, because a lot of this becomes a lot more powerful if you can actually say that um, the causal impact of this treatment is this, independent of communities. And I'm thinking both on your bias because you get people who are sick in this particular way, and that's the only people you're going to get. You're going to get some particular minority who does not follow treatment because they're just doctors, or are not present in U.S. population because it was done in certain cities that did not have that group.
Yep.
So it seems like you have a lot of power with embeddings. You can say treatment conditional on embedding,
Yep.
and it's
Exactly.
fantastic if you the embedding has what's called covariates that are causally affecting your treatment selection. It's bad
Mhm.
if the embedding has confounders that are kind of causally affected by all these phenomena.
Yep.
How do you even attempt to disentangle this kind of stuff, because it can be extremely powerful if you can do it?
Yeah. I once kind of have a minute, debate with David Bly on exactly causality. I would say that we can talk hours just on
Yes.
causal RWE. But let me highlight a few thoughts and love to pick you guys' brain as well. Is that um, number one, I would say that a lot of the original causal reasoning, all the tools and so forth, right, including Judy Pearl's great work, they are basically happening in the classic statistics setting where you have a few variables, right? You have a few
Mhm.
covariates, and you often make all kinds of assumption about whether all the confounders and all that, right? A lot of those tooling, frankly, to the best of my knowledge, start to break down in the high dimension place, right? So I think we really sort of need some sort of like high dimensional causal theory to some extent, right? So ultimately, what we really care about is counterfactual prediction, right? So if you can predict counterfactual right, that means that we actually deal with the spurious correlation, right? So I think that at least point us to a way to both train such a model and also evaluate such a model in a rigorous way, right? So that's maybe point number one. Point number two is that there is also a question about obviously interpretability to some extent, which is like if I can have a new embedding that perfectly separate a responder versus a non-responder for Keytruda, right? What does it tell me, right? So I could stratify patient, great. I can maybe have a companion diagnosis and so forth. But on the other hand, how does that help, like drug discovery, right? So in the very far future, I can even imagine we can exactly reason in the embedding space to say, hey, I can train a drug embedding, right? And then I can say, oh, this is where actually this is the best drug that work on this non-responder and so forth. So I can see we could go in that direction. Probably in the very short term, we still have to see whether we can distill some of the features, discernible known variable from the embedding to say, hey, that's actually the big difference between these two subgroups, right? So I think that could be the short term solution, but then in the very long term, it would be exciting to reason actually purely in that high dimension embedding space.
Yeah, I think the question I would have is, so first of all, this is extremely general what you're saying. I'm thinking I want to do carbon accounting. You have to say, what would you have done if I didn't pay you money? What if if I did pay you money? Counterfactual all over the place, high dimensional space. Any kind of forestry studies. They use samples when you stratify the population of trees in that case, and for every stratum you take samples. If your strata are wrong or not transferable, well, you have a bad sample. It's highly biased. And it seems like the core requirement is I want a biased model. In fact, all that our models do is creating bias. That's the training process. What I want to make sure is that it shouldn't be biased in a way that prevents me from transferring from my training population to my test population. So I have to know what the difference is, what biases I've baked in there, and what biases I do not want. So I want to separate out the training to the test versus what is actually preserved, like the laws of bodies.
Yeah.
And that's really my question. How can you separate those two regions of the dynamic space? Preserved, not preserved.
So actually, fortunately, like aside from computer science, right? So this is a holy grail in economics, right?
Oh,
This is
I
also
forgot
holy
about that one.
grail.
Yes.
Yeah,
And
in STEM. Yeah. So basically, long story short is that there are at least 3 big community who have to deal with this kind of problem. There are also lots of exciting thing like natural experiment, right? So can you leverage some sort of like kind of like events, right? That really essentially basically doing some kind of randomization in some sense, right? So that that it has nothing to do with the treatment decision and so forth. So I would say that this is still a very kind of like young thing, especially when you look into the causal real world evidence field, right? So, and I have some fun chat with some Harvard economists and other folks. So I think this will be very exciting area. But one very rudimentary way that we did right now is exactly what you talk about, right? So which is that we basically just try to do some very simple regression way to essentially kind of like normalize this two distribution, right? The case arm and the control arm. Make sure, because that's really a fundamental challenge, right? You don't want them to be biased towards by any variable that might impact the treatment response, right? So of course, at the beginning, you don't know what are those variables. You have some very obvious one, right? Candidates, and you have a lot more once you go into the high dimension space. And how do you actually try to make those two distribution similar as possible? So I would say that one thing I want to caveat here is that I'm not saying that any of this, I don't believe any of this can completely eliminate the confounders, but it could hopefully eliminate sufficiently well so you don't generate crap hypothesis left and right, right? So you generate some more valuable hypothesis, and then you can then help minimize the expense in the RCT. So you might be able to run a much more nimble, adaptive RCT.
Got it. Yeah, that actually helps a lot as a way of going forwards. Yeah, thank you, and thank you for taking the extra time.
Yeah, thanks so much.
Yeah,
Also really appreciate all the great questions. They are
absolutely.
awesome.
Yeah, excellent. Yeah, have a great rest of your day.
Okay, thank you. Bye now.
Bye.